Picture this. You are fitting a handle onto a cabinet door. You drive a small screw. The drill goes a fraction too long, and the screw head sinks past the surface. The hole around it begins to strip. The screw spins without catching. There is nothing to grab and no way to start again. Most people who have driven screws with a power drill have experienced something like this at least once. Now look at the ring of numbers on the collar of any standard drill. They sit there on almost every drill ever sold, from the cheapest to the most expensive, and most people either ignore them entirely or assume they change power or speed in some way. They do neither of those things. The ring is solving a specific problem, and understanding what that problem is changes how every screw driving job looks. Let's get into it right here on Small Things. What those numbers are actually setting. The ring of numbers on a drill collar is called the clutch, and it controls one thing: how much rotational force the drill applies before it stops driving. Every screw has a point at which it is correctly seated. Drive past that point and the screw head strips, the material crushes, or the surface is damaged. The clutch lets you set a force limit in advance, so the drill stops automatically when that limit is reached rather than relying on the operator to release the trigger at exactly the right moment. A lower number means the drill stops at lower force. A higher number allows more force before stopping. At the highest setting, the clutch disengages entirely, and the drill applies full power without stopping. Why this feature had to be invented? To understand why the clutch matters, it helps to think about what driving a screw by hand actually involves. When you drive a screw with a manual screwdriver, your hand is the feedback system. You feel the resistance change as the screw tightens. You feel the moment when the head is flush. You stop. The process is slow and imprecise, but the built-in feedback of your hand and wrist prevents most overdriving because you feel it coming. Early power drills removed that feedback entirely. The motor drove the bit at whatever torque it could produce, and the only way to stop was to release the trigger. In the early days of power tool use, this worked well enough for drilling holes, where the depth of the hole was the only concern. But when drills began to be used for driving screws, the absence of any limiting mechanism became a real problem. A motor that produces enough torque to drive a large screw into hardwood will destroy a small screw in softwood in the same fraction of a second. Every screw driving task required constant attention and precise trigger control, and mistakes were common and often irreversible. Black & Decker addressed this in 1946 by patenting a drill with a mechanical clutch built into the collar. The mechanism allowed a user to set a torque limit before starting, so the drill would stop driving automatically when the resistance reached the chosen level. The operator could focus on positioning and alignment rather than on monitoring the feel of the bit. The design was practical and effective, and it spread quickly through the industry. Within a few decades, the adjustable clutch collar had become standard equipment on virtually every drill designed for general use. The physical form of the mechanism and its position on the collar have changed very little in the years since. What changed was the scale of what drills were used for. As power tools became affordable through the second half of the 20th century, they moved from professional workshops into homes and garages. Millions of people who had never used a power tool before were now driving screws into furniture, hanging shelves, and fitting cabinet hardware. All of this involves small, delicate fasteners, where overdriving is the most common and most irreversible mistake. The clutch designed for professional use became essential for amateur use, and it has appeared on virtually every general-purpose drill sold since. The click you have probably heard. The sound a drill clutch makes when it disengages is distinctive. a rapid clicking or ratcheting noise that starts the moment the drill stops driving. Most people who have used a drill have heard it, but fewer know what is producing it. Inside the collar, behind the numbered ring, there is a spring. Rotating the collar to a higher number compresses that spring. Rotating it to a lower number relaxes it. The spring presses a plate against a set of small ball bearings. Those ball bearings sit in matching seats in the drivetrain housing. As long as the motor can turn the bit without the resistance exceeding the spring force, the ball bearings stay in their seats and the drivetrain spins as a connected unit. When the resistance on the bit rises, it pushes back through the drivetrain. If that pushback force exceeds the spring force holding the ball bearings in place, the bearings are displaced from their seats, and the drivetrain separates. The motor continues spinning, but the chuck stops. The ball bearings skip over the teeth in the housing, creating the clicking sound, until the trigger is released and the spring pressure reseats them. The user has not released the trigger. The drill has not stalled. The motor is running normally at full speed, but the mechanical connection between the motor and the screw has been broken by the geometry of the spring and the ball bearings, and the bit has stopped moving. The resistance at the screw reached the threshold. The clutch responded. The screw is protected from being driven further, and the material beneath it is protected from the force that would have kept coming. Switching the collar to drill mode bypasses this mechanism entirely by moving the plate and ball bearings out of engagement. In drill mode, no amount of resistance will disengage the drivetrain. The motor drives the bit until the trigger is released or the bit stalls, which is exactly the behavior needed for drilling holes through hard material, but exactly the wrong behavior for driving a small screw into soft wood. The numbers are not a shared language. There is something intuitive about the idea that setting a drill collar to 6 means applying a specific, repeatable amount of force, that the same setting should produce the same result on any drill of any brand. That intuition is wrong, and acting on it causes problems. The numbers on a drill collar are relative steps between the lowest and highest torque that particular drill can produce. The range varies considerably between brands and even between models from the same manufacturer. A drill with 11 collar positions spreads its available torque across 11 steps. A drill with 24 positions spreads it across 24. The numbers do not correspond to any shared standard. This means a setting of 4 on one drill may be roughly equivalent to a setting of 8 on another, or it may not be equivalent at all because the total torque range is also different. Two people with different drills following the same instructions will not necessarily get the same result, even if they use the same number. The only reliable approach is to start at the lowest setting, drive a test screw into the same material you are working with, then increase by one step at a time until the screw seats correctly without sinking past the surface. That process must be repeated whenever the task, the material, or the drill changes. The numbers are a dial between less and more, calibrated only to themselves. They are a starting point for a test, not a specification that transfers from one drill to another. When precision becomes a production problem. Today you will find the clutch doing two quite different jobs depending on where it appears. In newer consumer drills, the mechanical spring and ball bearing clutch is increasingly being supplemented or replaced by an electronic version. Instead of a spring setting a physical threshold, a sensor monitors the motor current. When the torque rises enough to increase the current beyond a set point, the electronics cut power to the motor. The mechanical clutch reacts at the moment the force threshold is reached. The electronic version reacts a fraction of a second later, because the sensor measurement, signal processing, and power cut all take time. For most tasks at home, this delay is irrelevant. For fine joinery or cabinet fitting, where the difference between correctly seated and overdriven is measured in fractions of a millimeter, experienced users often prefer the immediate mechanical response. In industrial assembly, the same principle operates at a completely different scale. Automated screw driving systems in manufacturing use precision clutches to ensure that every fastener in a product is seated to the same specification. A car door panel may contain dozens of screws. A smartphone assembly line may involve hundreds per device. If the clutch on the driver is set incorrectly or if it drifts over time due to wear, every unit produced in that window is potentially defective. The margin for error in production is far smaller than anything a home user would notice, and the cost of that error multiplies across thousands of units. Teaching a powerful machine when to stop. So what do those numbers on the collar actually do, and why does this tiny feature matter? Think about that cabinet screw again. The one that sank too far. The one that's stripped. The numbered collar is not there to make a drill more powerful. It is there to teach a powerful machine when to stop. The spring inside sets a limit. The ball bearings enforce it. The clicking sound is the drivetrain disengaging the moment the job is done before the job is undone. Sometimes the smartest engineering is not about adding more force. It is about knowing exactly when enough is enough and doing it automatically every time, regardless of how tired the operator is or how fast the job is moving. If this changed the way you look at the collar on your drill, let us know in the comments what you want us to explore next. We might make it our next episode. Thanks for watching. History often hides in the smallest details.